till the last lecture, we have learned some major concepts of circles, especially involving radical axis, radical center, orthogonal circles. And towards the end, we learned what is coaxial system of circles. And today, we will continue from where we left, and then we will also learn what happens when 2-3 circles interact with each other, and what happens when combination of 2 circles and problems based on these ideas come. Okay. So, let us start. So, this is a quick recap of the last idea that we touched, which is the coaxial system of circles. So, the simplest form of equation of coaxial system of circles can be written in this form. Now, the speciality of this system is all centers of these circles are on x-axis. Let us say this is x-axis, this is y-axis, and there are circles having the centers on x-axis. That is the first data, and also the radical axis of all these circles is the y-axis. So, we can get circles in the left side also. Here circles can be bigger circles like this also, okay. But the radical axis is the common radical axis, which is y-axis. And next, that is the same thing. Now, here in this case, if C is greater than 0, we get intersecting system, C equal to 0 touching system. For C less than 0, it is intersecting system. So, for C greater than 0, we get non-intersecting system. This we understood last time using the idea of the radius and also the center. Okay. So, we learned this in the last lecture. Now, there is a concept called as limiting point. Okay. So, what is the limiting point? We can understand limiting points as the point circles which are also part of the system and which are the limiting cases of the circles. That means beyond these points, the circles will not progress. Okay. For example, I will just take an example here. Let us say we have one system here, and let us say there is a point here. Beyond this point, the centers of the circles cannot progress. Okay. So, we can have circles like this, we can have circles here also. Similarly, here we can have circles, but beyond this point, centers will not progress. These points are called as the limiting points. Now, how to understand these limiting points? So, first let me erase this and go to the earlier slide. So, here when we converted this equation into an equation of family, we got an equation like this. So, here x equal to 0 is our radical axis and x square plus y square plus c is one of the members of the family of the circles. Now, when we checked for the points of intersections, that is when we substituted x equal to 0, we got y square equal to minus c. Now, based on this analysis, we concluded whether the system is intersecting or not. So, now this is one idea that you should remember. You need not remember these steps, these statements, but you remember this idea, because the idea will stay forever. Once if it is formed completely in your mind, then it is so resilient and strong that you can never erase it. Okay. So, while solving problems, we can just use ideas and solve problems. Now, coming to the limiting points case, if we take the same equation, which is x square plus y square plus 2 lambda x plus c equal to 0. Now, the center of this circle of this entire family is going to be minus lambda comma 0. This is the center. Now, because lambda is parameter, it will change. Now, when I take the radius will be lambda square minus c. Okay. So here in this case, lambda square minus c must be non-negative for the radius to be a real number, because if the value under square root is negative, then radius will come out to be complex, which means circles are non-existent. Okay. So for circles to exist, lambda square minus c must be non-negative. Now this will give us an idea that lambda square must be greater than equal to c, or if we just check the entire interval for lambda, lambda will be belonging to minus infinity to minus root c union root c to infinity. So that means on x-axis, if we observe, let's say this is my x-axis as number line. Now this is the root c and this is the minus root c. So the value of lambda cannot go beyond these values. Value of lambda cannot go beyond these values, and these two cases are the limiting cases for the lambda for this system to exist. Okay. So those limiting cases values of lambda are taken as the limiting points for this system. So that means on x and y axis, if we check the circles, okay, so I hope this is clear to you. So I'll just erase this and write this again. Okay. Now on x axis and y axis, when we take the circles of this family, the centers are minus lambda comma 0. So for lambda, the limiting cases were minus root c and plus root c. So when we put them there, we get these points which are the limiting cases. Okay. So basically these are the centers of the circles beyond which the circles cannot progress. Okay. So in case if any system, if you are asked to find out the limiting cases, then you can just apply the idea that radius must be real and you can get it. Okay. So here when we take the concept or the idea of coaxial system itself, it is slightly above the line when it comes to the syllabus of IIT-JEE. Okay. It is slightly borderline concepts. Sometimes questions involving other concepts may come as part of this concept, but still we try to touch some borderline concepts to make sure that students are always equipped with enough knowledge to attempt questions. Okay. So we will not go much deeper into this concept. We will solve few questions, develop some problem solving skills and then move on. Okay. Now there is one more concept called as mutually orthogonal coaxial systems. Okay. Now this idea of two systems which are orthogonal to each other is also slightly borderline idea, but still we will learn it at the basic level. Okay. Suppose let us say we have one system x square plus y square plus 2 lambda x plus c equal to 0, and we have another system here. If you notice here y term is absent, that means centers are on x axis. Here if we notice x term is absent, that means centers are on y axis. Now these two systems are always orthogonal. Okay. In a way, here if you notice, we have designed systems such that one system has centers on x axis and y axis as radical axis. The other system has centers on y axis and x axis as the radical axis. Okay. So these two are those systems. Now here also if you notice the constant term, one equation has plus c, other equation has minus c. So this way when we apply the condition for orthogonality, these two systems always come out to be orthogonal systems. Okay. Now how did I arrive at this? For that we can go for one hit and trial approach. Let us say I have taken a system of circles which have centers on y axis, but a constant k is taken for c, which is supposed to be the constant, and here mu is the parameter. Now for this system to be orthogonal with this system, we will apply the condition for orthogonality and then we will get k equal to minus c only. So that way these two systems are perfect fit into each other, which are mutually orthogonal. Okay. So now these systems may change their orientation depending on the situation. So we'll have one simple idea of that, one simple discussion of that systems, how they are oriented on geometry also. Okay. So suppose, let's say, if I take the original system, to be a system like this, I'll do it here. Let's say this is my y-axis, this is my x-axis. Okay. Now, if I take the original system to be a touching system, touching at y-axis, so we can get many circles which are touching y-axis exactly at the origin. So you can get many circles here. Similarly, this side also we can get many circles. Okay, we can get infinite circles. Now, this system that I have drawn in black color can be written as x square plus y square plus 2gx or 2 lambda x, it does not matter, plus c equal to 0. Okay, because we are following lambda, let me just make sure that it is only lambda. This is lambda. Okay. So here the centers of all the circles will be at minus lambda comma 0 depending on the value of the lambda. Okay. Now because here circles are touching y-axis, the c must be 0 because circles are touching y-axis. I have taken one simple case. First understand this case, then I will connect all of them. Okay. Sometimes in my lectures, I am also intentionally using a kind of fuzzy logic. Okay. That means if sometimes we go from step 0 to step 100 systematically, sometimes we hit the steps randomly and then we connect all of them, because this kind of abstract logic is also very much required for students to master mathematics. Okay. So try to understand. First I am taking an example. Now go deeper into this example, understand it, then we will connect with all other examples. Okay. So now at c equal to 0, because c equal to 0, this is a touching case. Okay. Now if c equal to 0 is given, that means centers of these circles can come till origin, that is the limiting point. So here in this case limiting points are the limiting points is the origin. Okay. Now if I take another system which is on, let us say, y-axis, which is in red color. Okay, this system. I hope it's clearly visible to you. Both colors, black and red. Now the black system and red system are mutually orthogonal to each other. So if you take any member from one system and any one member from other system, if you check these two, whenever they cut, wherever they cut, they will be orthogonal. Okay, that is the main idea of two mutually orthogonal systems. So here the equation of this system can be written as x square plus y square plus 2 mu x minus c equal to 0, which is what we have just stated earlier. Okay. So now when you apply orthogonality condition on this, anyways it will be proved algebraically. Okay. So now I will take another case. Okay. Suppose let us say here I am taking the system in blue. This is x-axis, this is y-axis. Now let us say I take a system which is apart, okay, which has limiting points. Let us say this limiting point is root c comma 0, and here the limiting point is minus root c comma 0. Because here I am talking about square roots, so that means c must be naturally positive. Okay, so I will just do it here. C must be naturally positive. Okay. If c equal to 0, these two limiting points will come closer to origin. If c is greater than 0, if c is increasing, then these two limiting points will move far from origin. So limiting points, what these points will do, they will limit the circles. So here for examples, we will get circles here, we can get circle here also, but this point is the limiting case. So, we will not get circles beyond this point. Okay. Similarly here, if we just go only for the circles passing through this point, we can get circles like this, but there could be circles here also. Okay. Now, this is one system. Now, if we take the other system which has centers on y-axis and also having x-axis as the radical axis, that system can be represented in red color like this. So, through these limiting points, the circles will pass for the other system. This is the natural idea of these coaxial systems of circles. Okay. So, the diagram is not that great, but you can understand how the circles will behave. Okay. Now, the other case, if let us say the circles on y-axis have limiting point, if these have limiting points, then the circles on x-axis will pass through these limiting points. So, then we will be getting circles like this. Okay. So, the system on x-axis and the system on y-axis, these two will be mutually orthogonal. This is just the idea. Okay. We do not have to go much deeper into this. You can remember that for every family, there exists an orthogonal family. Now, for the family which is written in this equation, for this family, there exists another family which is orthogonal, which comes in this form. You can only remember this part. Okay. So, this is all just for rough work and rough idea of how the geometry will lie. Okay. So, now that we have understood what are limiting points, what are the coaxial system, and how do they look like, now we can solve some basic problems on this. Okay. So, as I said earlier also, this is a borderline concept, much deeper questions will not come in on these concepts. Okay. So, here I will take blue color. So, one of the limiting points of the coaxial systems of circles containing the family is what? So, basically we have to find the limiting points. Okay. So, to find the limiting points, first we have to form a system. Okay. Now, here two circles are already given. Now, whether these two circles are intersecting or touching or apart, it does not matter. They should have one common radical axis. Okay. So, first we will try to find out the radical axis. So, here if we subtract one circle from the other circle, we will anyways get the radical axis. So, I am multiplying first equation with minus sign. So, which will give me minus x square minus y square plus 6x plus 6y minus 4 equal to 0, and second equation I am writing as it is. Basically, I subtracted first equation from second, because here I noticed that these minus 6 and minus 6x and minus 6y have negative sign. So, for algebra to be better, I just multiplied that with minus sign. So, these two get cancelled, and here we will be left with 4x plus 2y minus 1 equal to 0. This becomes my equation of radical axis. Now, if this is the equation of radical axis, then what would be the equation of the family? We have to take s plus lambda l. Now, what is the s that we can take? We can take whichever is the equation which has smaller numbers as our main circle. Okay. So, here 6, 6, 4, here 2, 4, 3. These numbers seem to be small. So, I am taking this. It does not matter which one you take. So, our equation of the family or the system will be x square plus y square minus 2x minus 4y plus 3 plus lambda into 4x plus 2y minus 1 equal to 0. Okay. Now, here if I club x terms and y terms and constant terms, I can further write this equation as x square plus y square plus x common, 2x common, I will get minus 1 plus 2 lambda, and if I take 2y common, I will get minus 2 plus lambda, and the constant term is 3 minus lambda. Okay. So, here we are getting plus 2x into something plus 2y into something. Now, what will be the center of this circle? Center of this system will be 1 minus 2 lambda, comma 2 minus lambda. That will be the center. Now, what will be the radius? Because the constant term is 3 minus lambda, radius can be written like this. Radius square is equal to the x coordinate of the center, y coordinate of the center, both to be squared and added. So, 1 minus 2 lambda square plus 2 minus lambda square minus 3 minus lambda. This radius must be non-negative. Okay. So, let me just check this. Okay. So, this radius, this r square must be non-negative. So, let me just work out with this. So, if we just square it and simplify, we get 1 plus 4 lambda square minus 4 lambda plus 4 minus 4 lambda plus lambda square minus 3 plus lambda. Now, here there are 5 lambda square. Okay. And how many lambdas are there? Minus 8 lambda here and plus lambda there. So, minus 7 lambda and 1 here, 4 here and minus 3 there. So, we got plus 2. So, we got an equation like this for radius. Okay. Now, this radius must be this expression must be non-negative. So, for that, whatever are the limiting values that I can get, that I can solve by directly checking this inequality. Okay, greater than or equal to 0. Suppose if I, let us say, factorize this and solve it. So, this must be 1 here. Okay, so minus, this seems fine. So, 2 must be here. So, slight change. Okay. So, greater than or equal to 0, which means lambda is belonging to minus infinity to 2 by 5 to 1 to infinity. So, what are the limiting cases here? These are the limiting cases, because the limiting points are also the points where the radius becomes 0 in these cases. Okay. So, because those are the point circles which limit the family. So, we are looking for point circles, which also means we can equate this to 0 and check, but to be on safer side, always look for the inequality where you will know from where the lambda is varying and where you will get the limiting cases. Okay. That way you will understand the variation in the radius also. Okay. So, here 2 by 5 and 1 for lambda, these are the limiting cases. So, lambda equal to 1 is one limiting case, lambda equal to 2 by 5 is one limiting case. Now, put these two values in the coordinates of the center and get the limiting points. Okay. So, if I put, let us say, lambda equal to 1, lambda equal to 1 will give me 1 minus 2, 2 minus 1, which is minus 1 comma 1. is it any one of the points? No, it is not. So we will put the other value and check. Okay, lambda equal to 2 by 5. So if we put 2 by 5 in place of this, we get 1 minus 2 into 2 by 5, this is the x coordinate, and 2 minus 2 by 5, this is the y coordinate. If we simplify this, we get 5 minus 4, which is 1 by 5, and here find 2 to 10, 10 minus 2 is 8, 8 by 5. So are we getting the one of the options, 1 by 5 comma 8 by 5, is it there? Yes. So this is the right answer. Okay. So this way we can solve questions on limiting cases. Okay. So I also placed another question based on this system of circles. We will try to solve this also. Okay. So you will get rough idea. Always remember, the first example that we solve does not clear the confusion. In fact, it increases the confusion. But the second problem that we solve will clear the confusion. Okay. So let's solve one more. For what values of L and M, these two, this family of circles belong to the coaxial system determined by these. So how to approach here? Now when these two circles, whether they intersect or not, it does not matter. So when they interact, there can be a family formed. So we will first form a radical axis here. So I will write the second equation as x square plus y square minus x by 2 is equal to 0. Now when I subtract one from the other, I get something like 2x plus x by 2 plus 4y minus 6 equal to 0. So this line can be simplified as 5x plus 8y minus 12 equal to 0. This becomes my radical axis. Now having the common radical axis, I have to generate one equation of family. Now which one is better to take, whether the first circle or the second circle, it's your choice. It should not anyways matter. Okay. So let's say I take the second case. So this is the equation of the system. X square plus y square minus x by 2 plus lambda into 5x plus 8y minus 12 equal to 0. Okay. This is the equation of the system which has the common radical axis. Till here it is fine. Now here it is mentioned that whatever is the equation of a circle here, which is mentioned in terms of two parameters which are L and M, this has to belong to the given system. So that means that equation must come in this form only. Okay. So what I will try to do is, I will try to convert this into standard form by clubbing the terms with same terms, similar terms, and then I will try to compare this with that. Okay. So here only I have to combine the terms with x. Okay. So here I am going to combine the terms with x. X square plus y square, this is the standard term. Now when I take x common, I am getting 5 lambda minus 1 by 2. 5 lambda minus 1 by 2. Plus when I take y common, I am getting 8 lambda. And the constant term is minus 12 lambda. This is the equation of the family or the system. Now I will write the member in the standard form. So because there is phi here which is multiplying x square and y square, to convert this into standard form we have to divide with phi. So it becomes x square plus y square, and there is no x term here. Okay. So that means x into 0 plus y into L by phi, and constant term is minus m by phi. This must be equal to 0. Now if you see, this is supposed to be a member, that means this is a fixed circle, but the above equation is an equation of this entire system. Lambda is parameter there. If I vary that parameter lambda, I'll get different circles. In fact, all circle I can get by varying lambda over all real values. But to get this particular member, I may have to fix lambda to one particular value. So basically, I am looking for existence of lambda for this fixation, or what happens to L and M if this is a member of that. So now for the second circle, second equation to be a member of the first equation, when we compare these two, for a particular value of lambda, I should be able to get the second equation. So by comparing, I'll try to evaluate lambda and I'll put lambda and verify L and M. Okay. So suppose here, if I compare the x terms, this phi lambda minus 1 by 2 must be 0. Okay. So from here, I get lambda to be equal to 1 by 10. Now I'll substitute lambda for other cases and see what happens to L and M. Okay. So when I compare y, 8 lambda must be equal to L by 5. Now lambda is already 1 by 10. So from here I can get L equal to 8 into 1 by 10, and when I take this phi to the other side, it will multiply. So at the end I'll get L equal to 4. Okay. Now in similar lines, I can also get M. Okay. So now when I compare the constant term, which is minus 12 lambda equal to minus M by 5. So from here I can get M directly. Okay. So M is equal to 12 into 5 into lambda, which is 1 by 10. So when I just divide it, I'll get M equal to 6. So here I got L equal to 4 and M equal to 6. Okay. So in this, if I vary L and M indefinitely, all circles may not be part of the system. But when I fix L to be 4 and M to be 6, then only this particular equation will be part of the system. Okay. So this way we can solve this question. Okay. So here in this coaxial system, what have we learned? What is the meaning of coaxial system and how to represent them using algebra, and how do they look like on geometry? Now, is there any special case there? What are the limiting points? How to calculate limiting points? Okay. And if there are two systems, for them to be orthogonal, what shall happen and how to derive? That's only thing that is there in this coaxial system of circles. Okay. Now we'll move on to the next concept, which is relative orientation of circles, or also we can call it as relative position of circles. Now, if let's say there are two circles, now these two circles may be apart, maybe they are touching, maybe they are intersecting, or maybe they are touching internally. Here they are touching internally, or maybe one circle is inside the other circle, or maybe they are concentric circles. So in all these cases are generally possible. Now in all these cases, how to identify which case is the set of equations that we got? Because whenever we solve any problem in this chapter, we basically have two algebraic equations in front of us. Now by looking at those equations, can we spot which case it is going to be? So that is our task from now onwards. Okay. So by looking at the algebra of the equations, we should be able to tell which case it is, and if that is identified as the case, then in that case how to proceed with the problem solving. So these things we are going to learn shortly. Okay. So here I have made a table. We will fill this table little later. Let's take case by case. Okay. Suppose let's say circles are intersecting. Okay. So this is a diagram which represents intersecting circles. So here C1 is center of one circle, C2 is center of the second circle, radius 1 is the first circle's radius, radius 2 is the second circle's radius. Now distance between centers, that is the C1, C2. C1, C2 distance between centers sometimes is also mentioned as D, D for distance. Now we have, whenever we look at any algebra of the equation, we have the centers and also the radii. Okay, so that is why the main focus is on the centers and the radii. Okay, for example, let's say there is one general equation, x square plus y square plus 2g1x plus 2f1y plus c1 equal to 0. So what is the first information that we derive from the equation? That the center is minus g1 comma minus f1 and the radius is root of g1 square plus f1 square minus c1. So this is the first information that we derive. Okay, so we can also call this as first information report, FIR. Okay, so looking at the equation, center and radius are the first things that we derive. So we'll bank mainly our analysis on centers and radii only. Okay, so let me just erase all this. So here the distance between centers, so here distance between centers is denoted with D. Okay. Now looking at these circles, can you compare R1, R2 with D to get a relation here? Of course we can get. Suppose if we take R1, now this distance, red, okay, so this distance is R1 and this distance is R2. So in a way we can say that D has to be greater than R1 plus R2 for the circles to be apart. Okay, apart means they are neither touching nor intersecting, they are separate. Okay, so that is the first condition that we observe. Okay, so what are the things that we need to make note of? The first is the condition. What is the condition? Which will help us identify whether the equations which are representing circles are touching or intersecting or apart. Okay, so that is the first step. Next step that you have to observe is how many common tangents are possible for that particular case. Okay, so here in this half an hour discussion, this discussion is going to be at least for half an hour. So please bear with me and stay focused. Okay, here we are going to analyze all cases at micro level, so that when you face any question in the exam, you get plan very fast. Okay, so here how many common tangents are possible? There are two types of common tangents here. One type which are passing externally and touching the circles externally, separately from outside they are touching, which are meeting at this point Q. So these two tangents are called as direct common tangents. Okay, we can in short form write them as DCT. DCT means direct common tangents. There are also tangents which I am marking here, this one and also this one. These two tangents are looking like transversal. Okay, so we call them as transverse common tangents. In short form, we can call them as TCT, transverse common tangents. Sometimes these common tangents are also called as cross common tangents because they are crossing. Okay, so when you look at the words, when you look at the terminology, generally you will anyways understand whether it is the direct one or the transverse one. So here in this particular case, there are two transverse common tangents and there are two direct common tangents. Now for a different scenario, for a different relative position, the numbers may vary. Okay. Now similarly, are there any common chords? Are there any common chords? Is it possible? Here common chords are not possible because circles are not intersecting. We get common chord only when circles intersect. Okay. So, common chord not possible. Is there any common normal? Of course, there is one common normal. In general, in circles, normal passes through the center of the circle. So, any line passing through the center is a normal. Now, for a line to be common normal to both the circles, it has to pass through both the centers. So, there is one common normal which is the line joining the centers only. So, common normal is there which is only one. Okay. Also, is there a way to find out the length of these common tangents? Is there any way to find out the equations of those tangents? That is our task. Okay. So, in this half an hour discussion, we are going to learn all of them. Okay. So, now let us go back to the table and let us complete this table. Okay. So, here understand the way I am filling this table and you try to make your own table. Okay. Do not take a snapshot, do not copy this, understand this and try to make your own so that you will remember it. Okay. So, first case which is apart, when circles are apart, the condition is D must be greater than R1 plus R2. Now, when circles are apart, how many direct common tangents are there? We just observed that there are two direct common tangents. And how many transverse common tangents were there which are going cross? There were two transverse common tangents. And how many common chords were there? There was no common chord and common normal was 1. Okay. So, this way we can fill the complete table. Okay. So, let me just fill it. If the circles are touching externally, then what happens? So, let us take that case separately. But I think I will give you 10 to 20 seconds time to think about this and try to work out. Okay. Just think and try to work out what is going to happen and what are the numbers that should come here. 10 to 20 minutes break. 20 seconds. Okay. Sorry for that. It is 10 to 20 seconds break. Okay. So, you might have already worked out in rough work. Okay. So, let us take that case with the diagram. So, suppose let us say if circles are touching externally, then two direct common tangents are possible and there is only one tangent which is the transverse common tangent which is passing between the circles. Okay. And common chord is not possible, common normal is only 1. Okay. So, with the diagram we can observe like this. Also, if I take the intersecting circles case, okay, there are only two direct common tangents. Transverse common tangents which are cross are not possible here, and there is one common normal, common chord which we can get by joining the points of intersection. Common normal exists. Okay. Suppose let us say I take another case where circles are touching internally. So, here in this case there is only one common tangent. We do not know whether it is direct or transverse, but there is only one. Okay. Because it is external, we can also call it as direct, that is fine. Now, if one circle is inside the other, common tangents are not possible, common normal is possible, but common chord is also not possible. Now, if circles are concentric, that means having the same center. Now, of course, common tangents not possible, common chords also not possible, common normals are infinite, because any line passing through the center is going to be a common normal. Okay. But what about the conditions? How to get the conditions here? Here, if we check the centers, okay, both centers are at the same point, we can say that distance d, which is distance between centers, is 0 for this case. Now, for the next case, if we observe d and the d, which is the distance between centers, and r1 minus r2, these two can be directly compared. Let's go to the next case and check. If they are touching each other, what happens to d and r1 minus r2? Just think about it, you will get the idea. Okay, so let's work out the conditions from the touching case, because this will be a systematic flow. Now here, this radius is r1, this radius is r2. So we get d equal to r1 plus r2 for the case where circles are touching externally. Distance between centers becomes sum of the radii. Suppose in this case, if I observe, so straight away by comparing with the earlier case, we can say that d must be less than r1 plus r2. But this condition does not suffice the situation. For that, we have to put another condition, which we will understand from this. So here, when I take the difference of the radii, so d is definitely equal to that difference. Distance between centers is equal to mod of r1 minus r2. Okay, that you can directly observe. Okay, so here the centers are not clear. So let me draw a separate diagram for you. Okay, let's say this is one center, and there is one circle here which is touching internally. Now, when I join radius through this center, then this entire distance is going to be, let's say, r1, and this small distance is going to be r2. So distance between centers can be written as r1 minus r2. So here in this case, d is equal to mod of r1 minus r2. Okay. So in this case, we can also put another condition that d must be greater than mod of r1 minus r2. Because if we just put only one condition, it does not guarantee the situation. So we have to put another condition. So this way we can derive the conditions. So for this, d must be less than this, and for this, d equal to 0. Now let's complete the table. So when circles are touching externally, d equal to r1 plus r2, this is the condition. If they are intersecting, d must be less than r1 plus r2. Also, d must be greater than mod of r1 minus r2. These are the two conditions. Touching internally, d equal to mod of r1 minus r2, and one inside the other, d must be less than mod of r1 minus r2, and concentric circles, d must be equal to 0. Okay. Now let's take the direct common tangents. So when touching externally, direct common tangents will be 2 and transverse common tangent is 1. Now if the circles are intersecting, we got 2 direct common tangents and no transverse common tangents. Now if they are touching internally, then there is only one common tangent. Remember the case? Touching internally, there is only one common tangent. So I'll write it in a box here. There is only one common tangent. Okay. And one inside the other, no common tangents. Concentric also, no common tangents. Okay. Now let's look at the common chords. Now if they are touching externally, no common chords. Only when the case of intersecting is taken, there is one common chord, and for all other cases, there is no common chord. Okay. Now common normals are always 1, except the last case where we get infinite common normals. Okay. So till here we have understood how many are possible upfront. Now as and when situation comes, we'll get the idea very fast in problem solving. Okay. Now further coming into this, how to find out the length of direct common tangents, transverse common tangents and common chords. This I will explain in the next slides. But when you are making the table, you will be completing this table. Okay. So here I will just write the formula here, but you will complete this on your own. Okay. This will be root of d square minus r1 minus r2 whole square, and this is root of d square minus r1 plus r2 whole square. For touching case it is 0. For this it is 2 root r1 r2, and for this it is the same formula, and here they don't exist. So this way we can do. And for common chord, we can find the common chord using the Pythagoras theorem. Okay. So that we will see when we take these special cases. Okay. So we will quickly look at these lengths, and then we will go on to find the equations of these direct common tangents, common chords, and what happens there. Okay. So let me just explain the lengths here first. Suppose let us say I have taken this case where two circles are apart. Now there is this common tangent which is the direct common tangent. Let us say I take this point as A, this point as B. I am joining the center, so it makes 90 degrees here because radius and tangent are perpendicular. So here also it makes 90 degrees. Now when I join these two, I will get D here. Now this distance is R1, this distance is R2. Okay. I am going to derive a formula only in terms of R1 and R2. Now if I do a construction here, let us say in blue line, a line which is parallel to the tangent but passing through one of the centers, then this side and this side are equal. So how much will be this marked side? It will be R1 minus R2, because from the complete R1 we are subtracting R2. Because these two are parallel, if angle at A is 90, this angle also will be 90. So we can take that diagram separately like this. This is 90 degrees and this length is D. This length is R1 minus R2, and I am interested in this, which is the length of the tangent. So using Pythagoras theorem, I can get this length as D square minus R1 minus R2 whole square. So this way I can find the length of the tangent. Similarly, so here I basically got this distance between P1 and P2, which is this distance. Okay. So that means I have found the length of direct common tangents using basic geometry. Similarly, I will also find the length of transverse common tangents. Suppose let us say if the tangents are like this. So from the center I am joining the radii. So it is R1, this is also R2. Now this is my distance D. Now I am making a construction in red through any center parallel to the tangent. Now here I have to extend this to complete the triangle. So how much distance have I extended? I extended R2 distance. So in this triangle, if we notice, this side is R1 plus R2 and this is D. I have to find this tangent. Now how do we do that? Again by using Pythagoras theorem, because there is 90 degrees here. So we can find the length as root of D square minus R1 plus R2 whole square. This way we can find the lengths of tangents. Now what happens if circles are touching? If these two circles are touching, then the transverse common tangent does not have any length, because it is only having one point on both circles. So here length will be 0. But direct common tangents will still have some lengths. Direct common tangents will still have some lengths. Okay. But this length can be found out by substituting d equal to r1 plus r2 in the earlier case. Okay. So for touching case, d is anyways equal to r1 plus r2. So direct common tangent can be calculated by substituting d equal to r1 plus r2 here. That will give us the formula of 2 root r1 r2. Okay. So here I have explained how to calculate the lengths of tangents using the pure geometry. Okay. Now let's say I am interested in finding the length of the common chord. Okay. I want to find the length of the common chord. Then how to find that? That we can find by finding the equation of the common chord. But for that, let me just go back to the table and explain you the equations. Okay. Now let me take a different color here. I'll take blue. Here, let's say we have numbered all of them, but let's say we are interested in finding the equations. If I want to find the equation of the common normal, then because we have concluded that all common normals pass through both centers, so if we just take the two centers and apply a 2-point form of straight line, we will get equation of common normal. So this entire segment where common normal is asked is very easy to calculate. Okay. Now what about this, where infinite common normals are available? So that means any line passing through the center is a common normal. So this is also very easy. Okay. So now let me come one column left. So here common chord is there. We get common chord only when circles intersect each other. Now when circles intersect each other, the common chord is nothing but the radical axis. So if we are interested in finding the common chord, we can just find radical axis and find the common chord. So whenever radical axis comes, I am writing RA. RA means radical axis. Okay. Now coming to the next. In the touching externally case, I have one transverse common tangent. Okay. If you still have any confusion, let me look at the diagram. So here this common chord can be calculated by taking the radical axis, because this is nothing but the radical axis. Similarly, this common tangent can be calculated using the radical axis. So here basically this is also radical axis. And for the case where they are touching internally, this common tangent also becomes the radical axis. This is also the radical axis. So wherever we got these singled out lines, all of them happen to be radical axis. So depending on the situation, we will calculate. But the cases where there are two common tangents, we need to have one standard method to calculate these common tangents. So let's name this as a star mark, okay, and we'll calculate it. We'll understand and develop a method for this star separately. Okay. So here I have explained you the table. If you want, you can take or note down the structure of this table. You can develop this table on your own once or twice, so that you will remember it later on. Okay. You don't have to learn these by heart. Okay. You don't learn them by ratta marfai. Learn them by only making them. Okay. So now our job is to identify how to calculate the equations of common tangents. So now I'll use this slide to explain you the equations of common tangents. So suppose here if I notice P1, P2 is my direct common tangent, and also Q1, Q2 is my direct common tangent. Okay. So now these two direct common tangents intersect at a point Q, which is also on the line joining the centers. Okay, because in circles, when we take two circles, the line joining centers will create a symmetry about that line itself. We can also take it as axis of symmetry. Okay. Now that means both transverse common tangents and also the direct common tangents intersect on the line joining centers. Now these points we named them as P and Q here. These points P and Q divide the line joining C1 and C2 in the ratio R1:R2. Now how did I confirm that? By taking similar triangles. Okay. Suppose let us say if I join this and if I join this. So I got two triangles here. This is one triangle, this is one triangle. I can draw these triangles separately. This is 90 and this is 90. These two angles are same. So hence these two angles must be same. If all three angles are same, and you know by definition that because radii are different, so triangles are definitely different, but angles are same. So that means these are similar triangles. So this is radius 1, this is radius 2. So the ratio in which P divides C1 and C2 is going to be R1:R2. Okay. So P divides the line joining centers C1 and C2 in the ratio R1:R2. Similarly, Q divides the line joining centers C1, C2 in the ratio R1:R2. These 2 points P and Q are also called as points of similitude. Points of similitude. These are also called as points of similitude. Okay. So here points of similitude means the points which divide the line joining centers in the ratio R1:R2 internally and also externally. P divides internally, Q divides externally. This is the general knowledge that we observed from the diagram. Now, what is the method to find the common tangents? The method is to find out the points P and Q first. That is the step 1. In step 1, we find the coordinates of P, coordinates of Q using centers and radii. And in step 2, we will use the method of finding tangents if points outside are given. Okay. So that way we can find the equations of tangents. So here I have explained an algorithm to find the common tangents. Now when we solve problems, I will explain the method and also I will work out and show you. Okay. So this is the way we find the equations of these 4 cases: transverse common tangents and also the direct common tangents. Okay. So with this we completed the theory part of this relative positioning of circles. Now whenever I think of the relative position of circles or relative orientation of circles, I only remember this table. So whenever I think of relative position, just table comes to my mind, and from the table I do everything. Okay. So if you want, you can take a snapshot. I will take a water break. Now based on this knowledge, let us solve some questions. So here this was a doubt sent by a student. Okay. So I am taking this doubt because there is something to learn in this for everybody. Okay. So here there are 2 circles whose centers are at a distance of 6 units. and also these circles are having 1 unit radius. See, I keep saying every day that beta, everything is about data. So, you should be able to understand and present the data in a proper way. Okay. So, here I am marking the important segments of the data. 2 circles with centers, distance between centers 6, radius 1 unit of each. P is the midpoint of the centers. C is a third circle which is touching C1 and C2 externally, and common tangent of C1 and C which also pass through P is also common tangent to C2 and C. Then find the radius of C. So, here if you notice, there is no equation of circle involved anywhere. Equation is not given. Coordinates of center are also not given. So, this question is pure geometry question. We can just kill it with Pythagoras theorem, similarity, congruency and all that. Okay. So, let us try to solve this. Okay. First, there are 2 circles C1 and C2. So, let me take one circle here. There is another circle. Okay. So, having radius 1 unit each. Distance between these two is 6 units. Midpoint of the centers is P. Midpoint is P, and there is a common tangent of these 2 circles which is passing through P. So, now if it is cutting the line joining centers in the middle, it must be the transverse common tangent. So, we have one common tangent here. Okay. So, imagine that it is touching here. Okay. So, let me just use an eraser here. Okay. Now, there is third circle which is touching both circles and also the common tangent. So, where could we fit that circle? There are 2 possibilities. One possibility is, I am drawing this in red. One possibility is, let us say circle is touching this circle and the tangent at somewhere here. If I take a circle like this, okay, it is not looking like circle, but if I take a circle like this, it is touching the first circle, it is touching the common tangent, but it is not touching the second circle. Because if this red circle is touching the blue line right here, then that means it cannot cross this line to touch the other circle. So, this is a wrong possibility. Okay. So, whenever we get any such thoughts, we can just draw at them and work out whether it happens or not. Okay. Now, the other possibility could be this. It is touching the circle and it is touching this circle also at the point where the tangent is touching. So, we can get a circle like this. Okay. This is another possibility. Now, this circle is going to be very big because it has to touch this circle and also this circle. So, it is going to be very big. So, in this particular situation, we cannot fit this. But I hope you have understood the overall diagram. Now, let us take this diagram in the next page. So, here I am taking circles vertically. Let us say I have one circle here which has 1 unit radius. And there is another circle here which also has 1 unit radius. Now, distance between centers is 6 units. There is one common tangent here. This point is P. Now, there is one third circle. Now, I am drawing this in red, which is passing through this point and also it is touching here. So, we can get a circle like this. Okay. So, now I hope the situation is clear to you. Now we have to find the radius of the red circle. Let's say the radius of red circle is r, okay, and we know the radii of these blue circles. This radius is 1 unit and this radius is 1 unit, and if I take this point as A, if I take this point as B, AB can be calculated assuming that the AB is transverse common tangent to these two circles, okay. Now what is the formula for transverse common tangent? We have just derived it to be root of d square minus r1 plus r2 whole square. Okay, so here if you notice, I am not using any equations of circles, I am using only pure geometry. Okay. So now further this can be written as root of, what is the distance between centers? It was given as 6 units. So 6 square minus r1 is 1 unit, r2 is also 1 unit. So 1 plus 1 whole square, which will be root of 36 minus 4, which is root 32. Also we can write this as 4 root 2, that is fine. Okay. AB is this. Now assuming that AB is the transverse common tangent to circle 1 and circle 2, I have calculated the length. But if we take this red circle and also this blue circle, for these two circles, AB is the direct common tangent. AB is the direct common tangent. And here these two circles are also touching. So for touching circles, what is the length of the tangent, which is the direct common tangent? It is 2 root r1 r2. We have just observed this. Now radius of this circle is 1 unit, but radius of this circle is r. So we can write this as 2 into root r. Okay. So there is a mistake there. Two root r into 1. Okay. Now this AB that we got by assuming that to be a direct common tangent for these two circles and transverse for those two circles must be equal. So which means 2 root r must be equal to 4 root 2. So from here if I solve, I get root r equal to 2 root 2, which will make r equal to 8. Okay. So this way we can solve the problem. Okay. So here if you notice, we solved this problem only by using the lengths of the tangents. Okay. So these are the applications of our clarity that we have developed with this tabular discussion. Okay. Okay, can we move on to the next question? Okay. Next question. Find the number of possible common tangents that exist for the following pairs of circles. Now this type of questions came in previous mains years also, previous mains papers. Recently, just 2-3 years back, I guess one question came. Okay. So now question is only about finding the number of possible common tangents. So it is just about understanding what type of relative orientation that we are facing with. Okay. So if I take the first question and if I take the first center C1, it is -3, -3. This is the first center. And if I take the second center C2, which is 1, 2 from here. Okay. Now if I take the radius r1, r1 is root of 3 square plus 3 square minus 14, which is 18 minus 14, which is 4, root of 4 is 2. So r1 is 2. Similarly, r2 can be calculated from the second equation. Okay. So 1 square plus 2 square, that is 5. Now 5 plus 4 is 9. Okay, I'll just write that 1 square plus 2 square plus 4, which is root 9, which is 3. So r1 is 2, r2 is 3. Now I'll try to find out the d, which is the distance between centers. So d will be -3 minus 1 whole square plus -3 minus 2 whole square. Now if we simplify this, it will be 4 square plus 5 square under root, which is also same as root of 41. 16 plus 25, it is 41. So now if I add 2 and 3, R1 plus R2 is 5, and if I check D is root of 41, which can be taken as 6 point something, because 6 square is the 36. Okay. So here we are getting D is definitely greater than R1 plus R2, which means the circles are going to be apart. If circles are apart, how many common tangents are possible? One here, and one here. Total we will get 4 common tangents. So for the first case, the answer is going to be 4. Okay. Similarly, for the second case, we can calculate the answer, but that I am leaving to you. Okay. So you can always solve it, and you can do it in the same way. Okay. Okay. So can we move on to the next question? So here, show that the circles touch each other, also find the point of contact and the common tangent at this point of contact. Okay. So how to do this? Can you make a plan? I will give you 5 seconds to make a plan. So here there are 2 circles. It's given that we have to prove that it is they are touching each other. So our first step is to check D, R1 and R2. So let me first take the center of the first circle. So here minus G minus F I have to extract. So they will be 2 and 3. So you know how I am calculating this. Here 2G is equal to minus 4 and 2F equal to minus 6. C equal to minus 12, and center is always minus G comma minus F. That way I am calculating it. Radius is root of G square plus F square minus C. Okay. Now similarly C2 is minus 3 comma minus 9. Now R1, which is the radius 1, is going to be 2 square plus 3 square plus 12, which is root of 25, which is 5. Okay. Similarly, R2 is root of 3 square plus 9 square and minus 26. So here we got 90 minus 26, which is 64, root of 64 is 8. So R1 is 5, R2 is 8. Now let me check the D. D is going to be root of 5 square and 3 minus minus 9, that is 12 square, which is going to be 13. And here it so happened that D has become exactly equal to R1 plus R2, because 8 plus 5 is 13, which is also D. So because D is equal to R1 plus R2, circles are going to be touching circles. Circles are going to touch externally. So that means total number of common tangents that are possible are going to be 3. But first we did the first part. Now let's see the other part. Also find the point of contact. We have to find this point of contact. So here if you observe, if you take the centers, join the centers, then the line joining centers will also pass through that point of contact, and from the center to this point the distance is R1, and from the second center to this point the distance is R2. So this point is dividing the line joining centers in the ratio R1 is to R2. So here we can also understand that the point of similitude, the point where transverse common tangents were supposed to intersect, is now the point of contact. Okay. So basically this is also the point which is dividing in the ratio R1 is to R2 internally. Okay. It is also the point of similitude. So we can get it by applying the section formula on the centers. Okay. So if I take this point as, let's say, P, so I can calculate P using section formula on these two centers. So they are dividing in the ratio 5:8. So I just have to take that ratio here. Okay. So for clarity, I will draw a diagram here. This is C1, this is C2, and this is P, which is dividing C1, C2 in the ratio 5:8. Okay. Now here the coordinates of C1 are 2, 3, coordinates of C2 are -3, -9. So the way we multiply is we send 5 to this side and 8 to this side. Okay. So P will be 5 into -3, which is -15, 8 into 2, which is the 16, by 5 plus 8, comma. In the same style we have to do for the y coordinate also. 5 into -9, which is -45, and 8 into 3, which is 24, divided by 5 plus 8. Now if we simplify, here we get 1 by 13, and here we get -21 by 13. So this will be the point of contact of circles. If you know that circles are touching, then you can get that point by applying the section formula, if they are touching externally. Now let me take a case. Of course we are solving the problem, but we are going tangentially outside using a different idea. Suppose if circles are touching internally. Suppose if circles are touching internally. You know the center of this circle. Also you know the center of the bigger circle. Okay, bigger circle center, let's say it is C1. And this center, let's say it is C2. Okay. Now you want to find out this point. Is there any method to find out the point? So if you join these two, you will get the line joining centers. And if, let's say, this point is P, if we join this, P will divide C1, C2, the line joining C1 and C2, in the ratio R1:R2 externally. Okay. This is also the point of similitude. Okay. So if circles are touching internally, then in general we are supposed to get 2 points of similitude, but in this case we will get only 1 point of similitude. Okay. So it is the same method, but external division can be used. Okay. So now let's go back. So this is given. Then find the, this is the third part. Find the equation of common tangent at this point of contact. Now when circles are touching, if circles are touching either externally or internally, if we want to find that common tangent at the point of contact, what is the best method? To find the radical axis. So here, if I just find the radical axis, that will be the answer. So how to find the radical axis? We have to subtract one circle from the other. Okay. So I'll take the equation like this. First equation is x square plus y square minus 4x minus 6y minus 12 equal to 0. The other circle is 6, 18, 26. So x square plus y square plus 6x plus 18y plus 26 equal to 0. These are the circles. Okay. So now we have to subtract one from the other. I am subtracting first equation from the second equation. So I will do it 2 minus 1, which will give me 10x, and here it will be 24y, and here 26 plus 12 will give me 38 is equal to 0. So if I just simplify it, Here I get 5x plus 12y plus 19 equal to 0. So this will be the equation of the required common tangent. So if they are touching and if you know it, if you know the geometry, you can find the common tangent using radical axis or using the other method. But here radical axis has sufficed. Okay, we will go for another question. Find all common tangents of the pairs of circles. This is the killer. This will have all possibilities. So how to do this? First, take the centers. Center 1 is minus 2 comma minus 1. Now center 2 is 2 comma 1. I have just calculated the centers. Now I will calculate the radii. R1 is going to be root of 2 square plus 1 square plus 4, which is going to be root of 9, which is 3. Also for the second one, R2 is going to be root of 2 square plus 1 square minus 4, which is 1. Okay. So I will just take a water break. So here we got centers and radii. Let's check the distance between centers, which is d is going to be minus 2 whole square plus minus 1 whole square, which is going to be root of 4 square plus 2 square, which is root 20. Root 20 is roughly greater than 4, but here sum of these two is 4. So we got the relation that d is greater than R1 plus R2. So circles are apart. So if circles are separate, then 4 common tangents are possible. Okay. So we get one pair of common tangents which are direct. We get another pair which are transverse. Now we know that both pairs intersect on the line joining centers only, and if we take these points as P and Q, these P and Q are the points of similitude. So now we have to find the common tangents directly. So now we will develop the method. So earlier the part that we skipped in the table, and of course we learned the method, I have explained the algorithm, but I did not solve any questions. That is this question. Okay. So here we are going to learn the method. Now let me take it to the next page. Centers are minus 2 minus 1, 2 1, radii are 3 and 1. Minus 2 minus 1 and radii, radius 3, and 2 1, radius is 1. Okay. Okay. So now if I plot these roughly, I will get one center here and the radius is 3 units. So we will get one circle here, something like this. And another minus 2 minus 1, so minus 2 here, minus 1, and the radius is 1 unit. So we will get another circle here. We got two circles like this. This is circle 1, this is circle 2. So here this is the radius 1, this is the radius 2. Okay. Now we want to find the points of similitude first. So how to identify that? By applying section formula. Okay. So if I join these two, there will be one point of similitude here P. There will be another point of similitude here Q. So we will find P and Q. I will do it for only one, you can do for the other. So let me do it for P. Q you will do. So let me give this as homework. Okay. So Q you will do, P I will do. Okay. So P can be calculated by applying the ratio, because it will be in the ratio R1 is to R2. So P can be calculated like this. this point is minus 2 minus 1, sorry, plus 2 plus 1. Okay, so there is a slight mistake in the diagram. Okay, let me just take the diagram again. Okay, so first this radius is 3 units and center is minus 2 minus 1. So the bigger circle is here and the smaller circle is here. Here the smaller circle is there. So this is my first center C1, this is my second center C2. Okay, so this is minus 2 minus 1 and this is 2 comma 1, and the ratio in which P divides is going to be 3:1. So I have to find P. So P becomes 3 into 2 plus 1 into minus 2 divided by 3 plus 1, comma, in similar way 3 into 1 plus 1 into minus 1 divided by 3 plus 1. Now if I simplify this, I will get 6 minus 2, which is 4, 4 by 4 here, and here if I simplify 3 minus 1, which is 2, 2 by 4, which will be 1 comma 1 by 2. Coordinates of P are 1 comma 1 by 2. Now through this point, whatever are the tangents that will pass, I have to calculate. So let me solve it on the next slide. So let's say there is a circle here. I will take any one equation of the circles. So I will take the second equation, x square plus y square minus 4x minus 2y plus 4. This is 4x. Okay, and the point, external point we got was 1 comma 1 by 2. Now if I convert this circle using completing square method, it can be completed into this form. Okay, so I basically added 1 4 and added 1 1. So I have to subtract, so this is equal to 1. This is the equation of the circle. Then the slope intercept form of tangent looks like this. Now if you have any confusion, you should go back to the first second lectures and check this. Okay, this is a shifted tangent in slope intercept form. So take the slope intercept form of the tangent and put the point directly in the tangent. So if I put this point 1 comma 1 by 2 in this, so I will get 1 by 2 minus 1 is equal to m into 1 minus 2 plus minus 1 into root of 1 plus m square. Our goal is to get the values of m here. So take all terms without square roots to LHS. So here we got minus 1 by 2, this is minus m. If we bring it here, we get m minus 1 by 2 is equal to plus minus root of 1 plus m square. Now square this. So we get m square minus m plus 1 by 4 is equal to 1 plus m square. So from this equation, we are supposed to get two values of m. Okay, because if the point is outside, when I draw tangents, I generally get two tangents. That means if I solve this equation, I am supposed to get two different values of m. But if m square is getting cancelled, which is the case that we are solving now, if m square is getting cancelled, that means you missed one solution. We are supposed to get two different tangents. We know that because the point is outside the circle. But because m square got cancelled, we were supposed to get two slopes, but now one slope is cancelled. So if m square gets cancelled, then we missed one slope. If such case arises, please remember that the slope that you missed is 1 by 0. The slope that you missed is 1 by 0. 1 by 0 slope means the line is parallel to y-axis. Okay, so there is one line that we have just missed here. Now the other slope we will get when I solve this. Okay, so m will become 1 by 4 minus 1, which is the minus 3 by 4. Okay, So by taking m1 equal to 1 by 0, that means we have to find a line which is parallel to y-axis and passing through p equal to 1 comma 1 by 2, which will give me the line x equal to 1. Because if it is passing through p and if it is vertical, x coordinate will remain constant. So x equal to 1 is the solution. And for the other solution, for m, which is minus 3 by 4, we will get equation of line like this. Okay. So here we will get 3x plus 4y, and here it is minus 2 and here it is minus 3. So which will give me minus 5 equal to 0. This way we can get the equations of tangents. Okay. So here this is one equation of tangent, this is another equation of tangent. Okay. So here if you observe, what happens is, whenever there is a point which is outside the circle, if you want to find tangents through that point which is outside, whether it is P or Q, point is outside, then the best method is put the point in the slope intercept form of the tangent, solve for m, put using these values of m, directly calculate the tangent using point slope form. Now when we do this method, there is a chance that sometimes by mistake or by luck or by bad luck, m square get cancelled. When m square gets cancelled, then what to do, that also I explained using this example. This example is beautifully picked only to explain this, because generally we get two values for the roots of m, we put them and we get the equations. But what happens when m square gets cancelled? When highest power gets cancelled in any algebraic equation, and if you are still interested in that root is 1 by 0. Okay. So with this we will close today's lecture. I hope you enjoyed today's lecture. We will meet again with more interesting ideas. Until then, have a great learning day. Learning shall never stop.